Hello, everyone, and welcome to today's webinar, Stretching the Limits of Microscopy Imaging with Deep Learning. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Leica Microsystems. To learn more, visit leicamicrosystems.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to now welcome our speaker, Hoyin Lai, Content Marketing Manager and Senior Application Specialist for Aivia at Leica Microsystems. Hoyin, you may now begin your presentation.
Hello, everyone. Welcome to the second webinar in our series in AI microscopy. My name is Hoyin. I'm the Senior Application Specialist with the Aivia team here at Leica. Today, we'll talk about ways to stretch the limits of microscopy imaging using deep learning. Let's go over today's agenda. First, we'll cover examples of a deep learning workflow for gentle long-term lifestyle imaging. Next, we'll talk about how deep learning training works in the realm of image processing. Then we'll cover the best practices for gathering training data so that you can start training a deep learning model on your own. And finally, we'll wrap up with a question and answer session. You can enter your questions in the comments window, and we'll go over your questions at the end of the presentation. When we run long-term live-cell imaging experiments, the most important aspect is to keep the sample alive. And from the data analysis perspective, the spatial resolution and the temporal resolution are quite important if we want to see certain rare events or interactions. Ideally, if we can optimize the spatial and temporal resolution on the microscope, we will be able to get the optimal data possible for analysis. But in reality, we would also have to take into the account of the sample viability to make sure that the acquisition settings that we are using are not going to cause the sample to become unviable. With deep learning, we could stretch the limits imposed by these three factors and get high quality data for long-term imaging without affecting the sample viability. So here's a couple of examples. There have been many developments that uses deep learning to improve and restore microscopy images. This is not an exhaustive list of applications that are enabled by deep learning. These are just the examples that are relevant to long-term lifestyle imaging. Let's take a look at the image on the left side. So this is about deconvolution. Deconvolution is a computationally intensive process that requires specialized knowledge to recover the original image signal. With deep learning, you can have the computer figure out the optical parameters and the image distortion profiles that are needed to apply the deconvolution. And when if we look at this image on the left, we have a neuron sample that is imaged on a resonance scanning confocal system that at a very high acquisition rate. And with the deconvolution deep learning model, we can reconstruct the image and improve the image quality. So if we see the image on the left, it is split between on the two sides. The left is the resonant confocal, and on the right is the deep learning restored image. If we look at the image in the middle, this is about denoising. Denoising is another process for improving the image quality by removing noise on the image and enhancing the contrast between the foreground and the background. And looking at the left side of this image, we have a noisy image that is acquired with very low light exposure. And with a deep learning model, we can recover the image signal using it, and you can see that on the right. And you can see the collagen matrix that is in magenta is much cleaner in this case. And beyond improving the quality of the existing data, you can also use deep learning to enhance the spatial resolution of the image, as you can see on the image on the right-hand side. Here, the deep learning model generates a super resolution version of the confocal image that is on the left side of the split. The resolution of the nuclear pore complexes in green and the microtubules in magenta are improved to a level that is comparable to that of STET on this image. Another super resolution example that I'm going to cover later in this presentation is going to use deep learning to simulate images from an expansion microscopy experiment. So here is an example of a deep learning denoising model in action. So this is a fixed sample of TOM20 labeled mitochondria that are captured on an iSIM system. On the left side, you have the raw image, which is acquired on very low laser power, and you can see that the mitochondria and the background it's not very different in appearance. And on the right-hand side, you have the ground truth image, which is acquired on high laser power, and it's been deconvolved to get the best possible image for the training the deep learning model. And when we train the deep learning model using the raw and the ground truth data, we generate a model that we apply to the raw image, and you can see the result of the model output in the middle. The label targets the mitochondrial membrane, and you can see that the membrane is recovered in the model output. And I'm going to play this video right now. So you can see that with the deep learning output, the background is is suppressed compared to the raw image, and we can also make out much of the details from of the mitochondria as well on this data set. So let's extend this to a live imaging application. So we have a U2OS cell with mitochondria in green and lysosome that are in magenta. Imaging mitochondria live can be a bit tricky because they're very sensitive to phototoxicity. And you will need much lower light exposure if you want to run a long-term imaging experiments observing them. But doing that, you're going to get images that are much lower in quality, and it's going to make the interactions between the mitochondria and the lysosome very difficult to see. With deep learning, we can recover much of the signal from the raw image. If we look at the normalized intensity profile, you can see a steep intensity drop-off in the raw image in the cyan as we acquire more image volumes. But with deep learning, which you can see in the arcan or the orange line, the intensity is relatively consistent with, throughout the imaging, and that allows us to observe the interaction between the mitochondria and the lysosome, as well as do additional image analysis on this. So look at the video on the left. You can see between the raw and the arcan denoise image is that we can see much more detail with the arcan restoration. And that would allow us to, again, observe the interaction between the mitochondria and the lysosome. Let's take a look at another example. So we have a labeled microtubule in a Jurkat T cell that has been activated by a anti-CD3 antibody that's on the glass slide. And what we want to observe here is the interaction between the microtubule and the adhesion of the cell onto the glass slide. And if we want to look at these microtubules in detail, we're going to need high resolution data. So one way to get the higher resolution data is to use expansion microscopy to physically increase the size of the sample. So then that way we can look at the details between different objects within the cell, or within the sample. But once you have expanded the sample, it is also no longer living, and that's going to make live imaging a little bit tougher. So to that, we did a two-step process to bring expansion microscopy into a live cell imaging with deep learning. So first, we apply a denoising model to improve the image quality in the time-lapse data set. And then it is followed by the model that applies the expansion microscopy to the image. And with this two-step process, we can image the sample live and increase the resolution of the data at the same time. So let me go ahead and play this video. This is really quick. So on the top, we have the ISIM, decon ISIM data, which you can see some of the microtubules that are on this data set. And at the bottom is the output from the two-step arcan that we just mentioned. And you can see at the bottom there is much more detail with the on the microtubules, and you can see the interactions between the of the microtubule with the bottom of the glass, with the glass slide at the bottom of the image much more cleanly. So besides a better looking image, what else is possible? Well, it is possible to get better analysis as well. So I'm going to start playing this video now, and I'm going to and what this is going to show you is an example of a way to use the deep learning model to enhance the resolution of the nuclear pore complexes. So I will use a deep learning model as input to this analysis workflow that I'm using as a pre-processing step, so I can enhance the quality of the image. Next, I'm going to apply this. In addition to applying the deep learning model, the output of that is going to be used for segmentation and the detection of the individual nuclear pore complexes. And you can see with that, with the deep learning model and in combination with the analysis workflow, I can get the individual objects and the individual nuclear pore complexes much more effectively. And of course, that could also be applied to other applications as well. So in this case, we use the deep learning model to help us improve the axial resolution of the nuclei in a developing embryo. So on the right side, you can kind of see that the resolution of the nuclei is much better, and the result of this is much more obvious when we apply segmentation to it. And so with the deep learning model that we've applied, we can detect the cells that are missing in the lower left corner of this embryo much more effectively. And we can also get cell shapes that are more representative of the actual nuclei in the embryo. And we can apply this model to a live data set that will allow us to not just reconstruct the embryo, but also track the individual nuclei and its development over time. Now that we've covered some examples of how deep learning works in real-life applications, let's talk about the operating principles for deep learning. So if you've attended our previous webinar, this would be a refresher for you. In traditional analysis, rules are created by humans and the data is put through a program and we will get the answers out of it. In AI framework, the concept is flipped on its head. We can provide the data and the answer in the form of ground truths, and the framework will come up with the rules that maps the input data to the answer. And when we get new data, we can apply the rules that are generated from the framework to produce the answers that we were looking for. There are many types of deep learning algorithm. So today, I would like to focus on one specific type called a convolutional neural network. It is commonly used in image classification applications. So for example, networks like UNet and Arcan uses this framework to create deep learning models. I won't go into many details about how each of these networks behave, but generally speaking, in a convolutional neural network, the input image is sampled into smaller blocks, and each block passes through multiple convolution layers to generate feature maps, which are abstractions of the image that corresponds to a certain shape or features. And some features can be prominently represented in the data, and those will have a greater weight. And in the learning process, the weights given to each feature block are iteratively changed until the input matches with the output. So let's say I have up here, we have an example of a picture of a robot. When it goes through a convolutional neural network, it is going to be sampled into multiple different blocks. And each of these blocks could be a feature map that is abstracted from the image. So for example, it could be one of the features that could be generated could be the segmented appearance of the robot's arms. And another one could be the flat surfaces that represents the robot's face and feet. So these could be some examples of feature maps. And these feature maps could also be processed further and subdivided and generate additional feature maps and so on and so forth for throughout multiple layers. So in each of these layers, all of the information from each of these feature maps connects the input directly to the output. And that's how a convolutional neural network works on principle. But how does it work in real life? So let me give you a quick example. So I'm going to show you the training process in Aivia, but you have other tools that are available that you can train the model just the same. So you start by specifying the training data, and you'll need two sets of data, the raw image and the corresponding ground truth. Next, we specify the network that you want to use, and you can tune the hyperparameter to adjust how the system learns. Then when you start the training process, the computer will handle the rest and give you a model output that you can use on other data sets. So let's take a look at what happens during the learning process. In a convolutional neural network, the input image, so that would be what's on the left side of this network chart, it will pass through the network to come up with a prediction output image, which is represented by the crystal ball on the right. Then when you look at the prediction, it will be compared against the ground truth. And the difference between the two is the prediction error in red in the bar chart on the left here. And during this the learning process, The network will then try to minimize the error and carry it forward for future predictions. And there are two key concepts that drive this process called gradient descent and backpropagation. So what is gradient descent? So you can imagine an error function is a landscape with many hills and valleys, and the current error rate is a location somewhere on this landscape. The goal is for gradient descent is to reach the valley or the local minimum from the slope that you're standing on. And when you reach the bottom of the valley, so this should give you the optimal parameter or weight that minimizes the error between your prediction and the ground truth data that you put in. And this process is done over many steps. And you can adjust the steps by adjusting what's called the learn rate, which would impact how quickly the training process converges to a minima, or if it ever does at all. But keep in mind that the value that, since we're talking about a landscape with many hills and valleys, the valley that you are in currently could be one of many, and there could be other valleys that will give you an even lower error rate. And throughout this training, the training process, the gradient descent process is going to be repeated multiple times. And with each iteration, it is possible that you can find a more optimum solution. And if we look at the graphic at the top, you can see the error chart can be represented by the U-curve, and the error rate is the red ball. And the gradient descent would try to reach the bottom of this U-curve by iterating for multiple steps. And that's gradient descent. Another key concept for learning in a convolutional neural network setup is backpropagation. This describes the entire process for which the weights at each layer is optimized. And the way that this works is the model works backward from the final convolution layer from the output using gradient descent to find the optimal weights for each element within the layer, then moving one step up from one layer up or one step further away from the output towards the input, and repeat the same process. And it will continue to repeat until you reach the input layer. And so as you can see on this image here, is that we start off from the top. We start off from the layer on the right-hand side, and it will iterate through each one. And over time, certain connections will be strengthened, and other will be weakened. And so over multiple iterative process of backpropagation, so you will the layers and connections are going to be continuously strengthened or weakened depending on the error output. And what you will get in the final product is a model that encodes the different weights and filters that transform the input image to the desired output. Now that we've covered the principle of how deep learning works, let's talk about how to gather data to train the model. I've put together a couple of best practices to help you get started. There are many types of network that have different training data requirements. Today, I want to focus on gathering data for training a convolutional neural network like a UNet or RCAN. For this type of network, you will need a paired image of raw data and ground truths. The raw data is your standard imaging protocol, so it can be tuned to minimize the damage to the specimen due to light exposure. However, it is recommended that you maintain a minimum signal-to-noise ratio of 3 and above, and anything below that, you could see more errors from the model output. The ground truth is the optimal imaging state for your sample, meaning that it has low noise and background signal along with the best resolution you can get possible. You can run deconvolution to get better quality outcomes, or other methods or computational clearing to improve the quality of your ground truth data set. The image should maximize the dynamic range and be free of any oversaturation and undesirable artifacts or debris. So on the left side of the slide, I have an example of what a raw and what the ground truth data set looks like. On the top, we have the raw image, which is quite a bit noisier, and you cannot make out as much of the details of the mitochondria. Whereas as the bottom image, we have the ground truth, which has much better resolution of for the mitochondria. You can actually see the membrane that surrounds each mitochondria, and it's has a good dynamic contrast between the background and foreground, and free of any noise or debris or oversaturation. And so when you have pairs of data that you're training with, it is important for the data to be aligned between the raw and the ground truth data. Here is an example of a model out at the bottom. You have an example of a model output that was trained on a confocal and set image of nuclear pore complexes. Looking at the area where the red arrow highlights, you can see that on the left side, we have a model output that is trained on data set that were not aligned. And the model was not able to resolve these 3 individual nuclear pore complexes as well that you can see in the red arrow. And then on the right side, you can see that when we align the data set and train the model, we can actually improve the resolution. And with that, we can actually see that instead of just one blur of nuclear pore complexes, there are 3 of those items. And when you're training a model to use on live imaging, it can be a challenge to get the image aligned. And for that, it is okay to use a sample, a fixed sample to image, and then deploy the model on a live data set, so long as the process of fixing the sample does not change the sample characteristics. But if it is not possible to properly align the data set at all, then you can also try to use simulated data as well. Next, train with a variety of data. This is important because it allows the model to recognize critical features. So some examples are images of different intensity distributions with different shapes or sizes or with different states. So for example, let's say I'm trying to use a model to improve the quality of a nuclei imaging sequence and for tracking nuclei division. I may also need to include examples of when the nucleus is undergoing mitosis to get the model to recognize all of these different phases. And so when I apply the model to a light sequence, which you can see here on the left, this is going to allow you to see the chromatin condensation in the nucleus and track the entire division process throughout the live imaging. And one last best practice, if you have a sample with multiple features or scenes, like different organelles in a cell, it is preferred that you train separate models for each of them, as this would help you get the optimal output from your deep learning models. So let's take a look at the example on the left side here. So the image on the left is processed with a generic model that is trained on the red, the green, and the magenta channels on the features that you see on this image. And on the right, it is processed with a model that is trained for each channel separately. And if we look at just the red channel output, you can see the specialized model resolution is much better than the generic model output. And in more extreme cases, the model may try to correct the data in a way that takes away from the fidelity of the data, which you can see on the left side and at the bottom. If you look at these 2 images, both actually came from the same nuclear pore complex raw image, but I used a different model on each of them. On the left side, the model that I applied was trained on the nuclear pore complexes. So, and this allows, with this model, the data actually sharpens to point-like objects. Contrast that to the right, where the model that I applied was trained on microtubules, which are long and filamentous. And when the model sees these point objects in the raw image, it tries to stretch them out like filaments. And you can see there's some small connectivity between some of these points that should not have existed. That is not good. And what are some examples of data that you should train separate models on? So for example, you have, if you're using different imaging modalities or acquisition settings, like magnification and exposure, objects that are of different shape profiles. So let's say you're both spots and filaments, or stains that targets different parts of the same object. So like say if you have a membrane stain and a lumen stain. And what I like to point out when I talk between the difference between this slide and the previous slide is that in this case, we want to train separate models when we want to train separate models and not blend the data sets from different sample classes together. So let's say if you have a raw data set for a wide field image and a ground truth data set for confocal, you can still train a model to transform the wide field images to confocal. But let's say if you have a raw data set that have both wide field and confocal images in it, and a ground truth data set for something like with STED, you are going to likely get bad outcomes from the training because the wide field and the confocal images look quite different, and the model may not be capable of identifying unique features that would allow it to enhance the objects that you're interested in to the ground truth data that you're looking at. So to summarize, here are the best practices for gathering training data for deep learning model training. Number one, pair raw data that are acquired using your standard protocol that is tuned to reduce damage to the sample with ground truths that optimizes image quality. Two, align the raw images and your ground truth images. Three, train with a variety of data that represents the different states the samples could be in. And finally, separate different object classes and train separate models for each class to get the best deep learning model output. And if you're curious about the applications that I have shown on this webinar, you can go to avia-software.com/demo to request a free trial of the software. And with that, I would like to thank everyone for your attention and move on to the Q&A session. Thank you very much.
Thank you, Hoyin, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. So let's get started. Our first question asks, what is the difference between machine learning and deep learning?
All right, yeah. So there is, we've been hearing a lot about both of these terms, so machine learning and deep learning. So and they both belong to a general concept of AI. So the difference between machine learning and deep learning is that in machine learning, you provide a couple of examples, and it works on smaller scale images, smaller scale data sets. So it involves having the human being there to making sure that identifying the features that they would like, and then it runs through like a specific set of operations to come up with the rules. And then in deep learning, rather than the human actually providing anything, any information about what they're looking for, you just provide the info. You just provide, excuse me, in the sense of the what we are doing with imaging is that you provide the raw data and the ground truth, and in deep learning, the software will attempt to find an answer and correlate them, and it uses a significantly deeper network, and it also generates a lot more parameters than is humanly possible, and that allows us to create a rule that is more robust compared to machine learning.
Great, thank you. Our next question here asks, what kind of system do I need to train a deep learning model?
Yeah, so for deep learning models, so typically what you will need is a GPU, a modern GPU that is capable of running deep learning. So most commonly used ones are the ones that are made by NVIDIA, but there are other hardware that are capable of doing machine learning as well. But in the context of the software that I presented, Aivia, we use a NVIDIA GPU that is CUDA capable.
Great, thank you. Another question here, can I apply a trained model to multiple images?
Yes, so with a deep learning model, it's similar to machine learning model, is that you can apply this to multiple images, and it also, because the rules are more robust, relatively speaking, you can also apply it to data sets that have that look slightly different, and perhaps in some cases it might be able to even identify things that it maybe has not even seen. So that's a really powerful aspect of deep learning, is that you don't have to come up with the rules, and you don't have to come up with the analysis protocol for each data set that you're working with. The model will attempt to do all of that for you, and it can apply it to a much larger scale than is possible.
All right. And our next question here, how do you align your images?
So how we do it is we have an in-house script that uses that shifts the pixels, so that shifts the image pixel by pixel to find the matches. But there are other ways. I know there's some tools that are in ImageJ or in Fiji that are available for doing the alignment. And in other cases for our ground truth data, we also use the same system as well. So For instance, for the when we were training the confocal to set model, we were using a system that was capable of imaging in the confocal mode and then also in the STET mode. So then that way the sample is fixed on the stage of the system, and that allows us to image them both at the exact same time. So that would be so if we're doing image alignment, that would be the most recommended way to do it. Yeah.
Great, thank you. All right, well, we'll go ahead and wrap up with that final question there. And I want to thank you again, Hoyin, for your time today and your important research. We'd also like to thank Labyrinth and our sponsor, Leica Microsystems, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period, will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. Labyrinth will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Goodbye.